Hi everyone, so we're going to look at solving initial value problem, particularly first order differential equation given as y prime equals to f of x, y. The initial conditions given as y at x naught equals to y naught. Okay, so you can solve this initial value problem using Euler Method, which is the simplest numerical method. The Euler Method is of order 1. But today, I'm going to show you how to solve using Runge-Kutta Method. Okay, Runge-Kutta Method is also one numerical methods that can use to solve this first order differential equation. Now, Runge-Kutta Method, or I can write as RK method, can be written as yi equals to yn minus 1 plus h summation j from 1 to s aij f of x n minus 1 plus cjh yj. So my I and j start from 1 to s. Okay, I'll tell you what is x later on, and yn is given as yn minus 1 plus h. The summation from I equals to 1 to s bi f of xn minus 1 plus cih yi. Okay, so this is the definition of Runge-Kutta Method. It seems a bit complicated, right, with all these equations and things like that. But what Runge-Kutta does here, similarly with the Euler Method, so if you look at Euler, okay, Euler Method start from x naught, y naught, and it wanna reach yi xi, where it's given as yi equals to yi minus 1 plus hf of xi minus 1 yi minus 1. Okay, so this is Euler Method. Okay, so it used the step size, we call it this h here, this is the h for one step, h. So if you have more than 1, then you can divide it into more n interval, and then you have to add h along. Okay, but for RK method, the concept is still the same. Okay, for RK method, you have a starting value. Similarly, you have y naught and x naught. Okay, this is my yn. Okay, in between you gotta find yi, and I have yi here, which I known as internal stage value, internal stages or internal stage. This is my big Y. Now stage here refer to the S here, so depends on your method how many stages the method has. That's what your Y will represent. And then you have your, similarly, your step size h. Okay, so if you understand this concept, we can look at how to write it. So if you look at Euler Method, okay, Euler Method is a method of order 1. Okay, so it's written in this form. We call it the butcher tableau. Okay, because the Runge-Kutta method that you saw earlier on has the coefficient A and C. So these are my A's. I'm writing a big matrix here, so it's big A. This is my C. This is be my B transpose. Okay, so what it means that if you have yi equals to yi minus 1 plus h f of xi minus 1, yi minus 1 here. So my A here depends anything that come before my f. So this is this one. The coefficient, the multiplication from h and f, the coefficient here is where my A is. Okay, but it has to be referred to the big Y, which is my internal stages. Okay, for Euler method, there is no big Y. Okay, there's only small y. So small y here refer to, this is for my update. My update refer to my small y. The small y here, the coefficient is 1, so 1. So that's where this 1 comes along here. Okay, so anything else is 0 because I don't have a big y. So if I look at, to make it understand better, let's look at another example. We have the Runge-Kutta method is called the explicit trapezoidal rule. Okay, the explicit trapezoidal rule is given as y1 equals to yi minus 1, y2 is equals to yi minus 1 plus h of f1. Okay, so what is my f1? The stage derivative, where my f1 is given as f of xi minus 1 plus h. I'm going to write 0 here, although multiplication by 0 is 0. I'll show you why I want to write that. And you have also f2, okay, it's a two-stage method, plus h1 y2. So the update yi is given as yi minus 1 plus h half f1 plus h half f2. Okay, so let me just remind you again on all these variable we have. So y1 and y2 is my internal stage. Yeah, write it slightly nicer. I'll write it here. So these are my internal stage. This one known as my big F here, we call it stage derivative. So where we have more than one, so for internal stages. And this small y here is my update. So what trapezoidal does, so it starts with x0, y0, or yi minus 1, the initial. It has two stages, y1, y2, and using this two stage, it will find yi for my xi. Okay, so now go back to this this defining equation again. I can write this in terms of called Boucher tabulo. Okay, Boucher tabulo, where it's given by this. Okay, these are my A, these are the C values, and these are the B values. Okay, A here refer to this internal stages. Okay, next to the stage derivative. So there's no stage derivative in y1. So I have 0, 0. Okay, for y2, okay, I have 1 coefficient. There's 1 here. Okay, next to my stage derivative. So I have 1 here. And for there is no f2, so this is 0. Okay, so A depends on the coefficient for internal stages. Now C here depends on the coefficient inside the stage derivative. So these are my C's. Okay, so this is my C1, this is my C2. C1 is 0, C2 is 1. Okay, I hope you're with me. Now the B here refer to your update yi. Now next to the coefficient for f1 we have half, and then for f2 we have another half. Okay, so if you understand this, the Butcher tabular for trapezoidal rule is given as 0, 0, 0, 1, 1, 0, half, half. Okay, why this is important? So sometimes you're given a Butcher tabular and ask you to derive this, what you call equation here, defining equation. So that's why we need to be alert. We need to know. Okay, for instance, you also have, let me give you one for, we call it explicit midpoint. Okay, explicit midpoint. So now I'm going to give you just the Butcher tabular and you try to write it out. Okay, so I have half, half, 0, 0, 1. Now these are called the stages. Okay, stage 1. These are called stage 2. Okay, so my first column here refer to my y1, y2. These are my c1, c2. This is the same thing, but this is my b1, b2. Okay, so to write this, look at, so we know there are 2 stages. So we have y1, y2. Okay, now I told you A here refers to the coefficient next to the stage derivative f1 and f2, but there is no f1 and f2 on my first row. Okay, so we only have initial. Okay, now look at the second row here. Okay, because I say my y1 numbers here refer to the stage, internal stages. Okay, the coefficient next to the stage derivative. So I have this one for f1, this one for f2. So start with yi minus 1 plus half h over 2, f1. Now there is no f2 here, so because it's 0. So you can write 0 f2, but I will not let you do that. Okay, now what is my f1? Okay, f1. Okay, you have f1 because it's 2 stages. You also have f2. Okay, f1 refer to the f xi minus 1. Now the c here inside this stage derivative for next to the function. So we have 0. So I have 0 h for y1 and f for the next one plus half h for y2. Okay, you don't have to write this. I just want to show you why there's 0. Okay, in other words, this is my f xi minus 1 comma y1. Okay, I don't have much time, but let's write it for yi. Okay, they refer to these 2 values here. So I have yi minus 1 plus understand how this works, so I have h of f1 for b1 and then plus 1. So h, I have 1 here for f2. So simplifying this, I have yi minus 1 plus, there's no, because it's 0, h f2. Okay, so this is defining equation for explicit midpoint. Okay, let's look at one more example. One more example here refer to the 3-stage. Okay, let's look at 3-stage Runge-Kutta method. The 3-stage Runge-Kutta method, so I'm going to give you the butcher tableau. Oops, it's not straight. Let me just put it straight. Okay, so we have 0, half, 1, half, -1, 2, 1, 6, 2, third, and 1, 6. So I want to write this 2 close to 2 thirds. Okay. Now, how write the defining equation for the 3-stage Runge method? Okay, so this is the question that I would like you all to do. So let's look at how to write this. So, like I said, we have 3 stages here. Okay, 3 stages mean what it means by 3 stages. 3 stages means I will have y1, y2, y3. This also makes f1, f2, f3. Okay, the coefficient inside here refer to my a's. These are the a's. These are my a's. Okay, and the coefficient in here is for C. These are the C. And the coefficient in here, these are the B's. B coefficient. The B coefficient contained inside my Y. Okay, this is the B coefficient. Okay, so it's not equal. I'm just saying that for this B here, when you are writing your Y, your update, you must consider this coefficient. When I'm writing the internal stages, which is my big Y, I need to consider this A coefficient. Now when I'm writing the stage derivative, my F, I need to consider the C coefficient. Okay, if you clearly understand that, we can start writing. Okay, start with Y1. Y1. Okay, look at my first row. First row here. So I have 0, 0, 0. Okay, so I can see that my matrix A is a 3 by 3 matrix. Okay, 0, 0, 0, half, 0, 0, -1, 2, 0. Okay, now, is there a coefficient A in the first row? No, so write yi minus 1. Moving on to the second internal stages. Now the second internal stage is here. Okay, so I have half. I have one coefficient A half. Now this one refer to my F1. So I have F1, F2, F3 for my each column. Okay, so I have yi minus 1 plus h, then I have half F1. F2 is 0, the coefficient A for F2 is 0, the coefficient A for F3 is 0. Okay, you stop there. Now moving on to Y3. equals to yi minus 1 plus, now we look at y3 here. Okay, so I have a coefficient for f1, I have a coefficient next to the f2 but no for f3, so I have h minus 1 f1 plus h 2 f2 plus 0 for f3. Okay, so I hope you are okay with that. Now let's move on with my f. So what is this f1, f2, and we need also f3. Okay, all this f1, f2, f3. So f1 is my stage derivative, so which is my f. xi minus 1. Okay, now look at here. My c. C, f1 refer to my c. C, these are the c. 0. Nothing. y1. Okay, stage derivative for y1. Now f2, you have f xi minus 1 plus I have half h for y2. Now f3 here, f3 refer to f of xi minus 1 plus I have a 1 here, h y3. See, in general, you can actually ignore this bracket. It's just half h minus h, half h, and h. But I'm writing this bracket so that you know where this coefficient comes from. Okay, now you have written this. These are all my internal stages and stage roots. Lastly, where you get your update or your approximation, yn refer to yi minus 1. Okay, now you can also write this as yi, so let's not confuse you, so stick with yi. Yi equals to yi minus 1 plus, okay, now the b for my little y here, so I have 1 over 6, 1 over 6 h of f1 plus h, now 2 over 3 for f2, and lastly I have 1 over 6. So this is what I need here, f3. Okay, so f3 here, f3 that you obtain here will be used when you want to find the update. Okay, so these are the defining equation for 3-stage RK method. So you can see that if you're given a butcher tableau in this form, okay, if you're given a butcher tableau in this form, C, A, B transpose, I can write the defining equation. Or if I'm given a defining equation here, I should be able to write down my butcher tableau, vice versa. Okay, so this is all about Runge-Kutta method that you have learned. Now, let's just quickly recall the Runge-Kutta method that you have learned before I end this video. So I have looked into few methods. So we are looking at RK methods. So which has in this form CAB transpose. Now when A matrix is strictly lower triangular, you have explicit method. So when A is not lower triangular, you have implicit method. Okay, so we have looked into a few RK method, explicit RK methods. Some of them were the Euler method, or the one Euler method given as 0, 0, 1. We have to look into explicit trapezoidal, rule given as 0, 0, 0, and then you have 1, 1, 0, half, half. These are the Butcher below. Okay, so look, it's lower triangular. Okay, lower triangular. Now we are going to look into explicit midpoint. Okay, given as 0, 0, 0, 1, 0, 0, sorry, 1 here. Okay, 1, 0, no. Okay, so 0, 0, 0, I have half, half, 0, 0, 1. Okay, this is my explicit midpoint. This is also lower triangular, so therefore it's explicit. Now explicit trapezoidal and midpoint, they are order 2. Now we have to look at 3 stage. Okay, explicit 3 stage RK method, or the Heon method. So given at 0, 0, normally you don't write all the zeros, but you can. Okay, half, half, 0, 0, 1, negative 1, 2, 0, 1, 6, 2/3, and 1, 6. Okay, there's something interesting about this Butcher tabulo that I would like to say before I end this video. So if you look at the row sum condition, okay, row sum condition for the C here. So this is 0. Now 1 plus 0 gives you 1. Okay, so meaning the C here, Ci here, depend on the row sum condition for my coefficient in method A. Okay, so if this is 0, this is half, half. Okay, now this is 0, now this is half, half. Okay, half plus 0 give you half. Now 1 here, right? So 2 minus 1 is 1. Okay, so you add the row for the A will give you the C on each row. Now B here, look at the B here, the addition for B1 and B2. So B here, the summation for my BI is equals to 1. Okay, half plus half, 1. 0 plus 1, 1. 1, 6 plus 2/3 plus 1, 6 equals to 1. Okay, now why this is, but this is not all the case. Okay, there are only few cases where the row sum condition and the B's not get 1, but most 90% of this Butcher tabulo, the row sum condition hold, so does the summation for the B holds. Okay, so this is my longest video ever on Runge-Kutta Method that I have shared. So please press the pause button whenever you are tired, and good luck in understanding Runge-Kutta Method. Leave a comment if you have any question and any further explanation, and I'll get back to you. Okay, that's all for today.